All right, hello everybody, and welcome to this video. In today's talk, I will be presenting Deepseek LLM, which is the first paper released by Deepseek. So this gives us the foundation of everything which is to come, which I will be covering in the future. That is to say, V1.5, V2, V3, and R1. Sorry about the poor lighting here, but it's close to my bedtime, so I can't be exposing myself to light. So let's get into the abstract. And to say it briefly, they use direct preference optimization, DPO, here in a two-stage fine-tuning process, which I'll mention at the end. And they also propose mostly the same architecture as is used in the open source Llama architecture. However, there are some modifications. Notwithstanding, the abstract is relatively bland, and most of the information which is worth reading is in the sections themselves. So let's just first start off with the data. And they use 2 trillion tokens in their data set, and they improve it with 3 methods. So the first one is called deduplication, and deduplication, as the name suggests, is just removing duplicates. And then there's also the filtering stage, right here, filtering stage. So during the filter stage, they focus on developing a robust criteria for assessing the quality of a document, and this involves a detailed analysis which incorporates both linguistic and semantics. So this gives a view of the data quality from an individual and global perspective. That's according to the paper. And lastly, there's remixing, and remixing is somewhere here, right here. So remixing, during this process, they adjust their approach to it, assess any imbalances or biases in the data. So this is in order to increase the presence of underrepresented domains so that the training data is of a higher and more uniform quality. So there you have it. We're training on 2 trillion tokens, and we have these 3 stages of data processing to ensure that it's of high quality. So deduplication, remixing, and filtering. Okay, so next we have our tokenization. So for tokenization, they use byte level byte pair encoding. So if you're familiar with byte pair encoding, this is similar. I don't know the details myself of BBP, but it's not worth going into those details since tokenization, unless that's what you really want to learn, is simply a preliminary step in your large language model anyways. And it's just giving you the IDs, which the large language model will understand when it takes as an input, because as we know, a large language model cannot read an English sentence. It must first be tokenized and converted to the relevant IDs. One thing which I will mention is they have a vocabulary size of 100,000. However, they add 15 special tokens afterwards. So these are the padding tokens, for example, the separator token, so in between sentences, and etc. But they also do change it at the end to 102,400, and this is only for, I guess, it being a power of 2, even though this is 100 times the power of 2. So it's for efficiency purposes, but we can ignore that. One thing that I will quickly note before we move on is pre-tokenization. So it's mentioned here. And what is pre-tokenization? It was first introduced in GPT-2, as I mentioned, and this is essentially using a regular expression before you tokenize your text in order to avoid different character categories from merging. So an example they give here is Chinese, Japanese, Korean symbols from being merged together, which has no semantic meaning, but if they occur somehow, or if the model misinterprets the text, then this could happen erroneously. Or another example would be having a word followed by a punctuation. So dog exclamation mark or dog question mark. If this happens often enough, then your tokenized word won't just be dog anymore. It'll be dog followed by the punctuation. So you always want to separate punctuation from the semantics, because we want to have one token representing the semantics for dog, but we don't want to fractionalize or segment this based on all the different types of punctuation. As you can imagine, if this was the case, then every word would have its exclamation type, its question mark type, its period type, and that is very redundant. Okay, so now that we have tokenization out of the way, we can get into the meat and potatoes, which is architecture. And they propose a 7 billion and 67 billion parameter model. Once again, both use the 2 trillion token dataset. And first thing that you notice is this difference here. So whereas the dimension size is double, the number heads is double, the KV heads is actually different by a factor of 4. So that's also non-trivial, but let's get back to the number of layers, which is different by a factor of greater than 3. And this is commented on in the paper. They didn't mention why this difference exists, but we do know why we have a larger than normal, which would be 2 size from 30 layers. So that is to say 30 transformer blocks to 95 transformer blocks. So this is because they maintain parameter consistency with other open source models, simply put, but furthermore, it facilitates the model pipeline partitioning used in training and inference. So when we have a pipeline, we segment the model across different devices in order to train in a sharded manner. And somehow this layer size facilitates this. So I didn't get into the details of that in particular, but now you know why we have a larger than normal difference in terms of the layers between 7 billion and 67 billion. Then they also use pre-norm. So pre-norm is different from what was used in the original Transformers paper, which is post-norm. So there's only 2 types. And all this means is that we perform layer normalization before we send our input or latent from the residual stream to the next transformer block. Whereas in the transformer paper, this was done after the transformer block. And, I'm sorry, I should rephrase this, not after the transformer block, after the attention head and after the feed forward neural network. Because in our transformer block, we have the mass self-attention followed by the fully connected pointwise feed forward neural network. And in this case, instead of having the norm after each of those two stages, it's before. And simply put, this allows stabler gradients in deep networks. And this is an empirical observation. There might be theory behind it, but I just know that's empirically true. But it's we're doing this with RMS norm as well, which is better than layer norm. I'm not myself sure of the difference between the two, but you can just think of them as centering the mean at 0 and giving a standard deviation of 1. And then in terms of the activation function for the feed-forward neural network, it's Swiglu, and this is another variation. So think of Gelu or Relu, but it's just smoother to facilitate training. And what I really enjoyed seeing, I guess this is just a departure from the GPT class of models, is the down projection and up projection stride. So when you go through the pointwise fully connected feed-forward network, normally in GPT models, you'll increase the dimension by 4, but in this one it's done by 8/3. And once again, nobody said that 4 is a special number. It's just because it's used in GPT that so many people use 4, but you can see in this case that 8/3 is used instead. And they use rotary embedding. So I don't know why they didn't call it rope, like the full name, rotary positional embedding. But anyways, this is done, and it's pretty much the state of the art for encoding the position, and it's also relative position, not absolute position. So, I mean, that's pretty standard. And what else did they use? In terms of the attention operation, this is very significant. Instead of using multi-head self-attention, they use grouped query attention. And very simply, if you don't know already, multi-head self-attention has, for every query head that is generated, a corresponding key and value matrix, whereas in grouped query attention, we share, and this is a hyperparameter, so you can think of it as similar to mini batch stochastic gradient descent, where we can tune our batch size. In this case, the group size will determine how many query heads will share the same key and value head. So if we have a group size of 2, that means is that if we have 8 query heads, then we'll have 4 key and value heads, and I'm using head and matrices interchangeably here. And what this means is that every 2 query matrices will share 1 key and value, and this is a classic memory compute trade-off. So you will lose in terms of diversity and representation because you have half as many key and value heads, but you'll have half as much memory requirement in your KV cache. This is what they use here. But if you know from my previous video, in multi-head latent attention, this has changed completely. But in this current version, we are using group query attention. And finally, we also have flash attention, which is just a hardware-aware method of improving the number of kernel operations during the attention computation. And yeah, it's just there, flash attention. So now let's move on to the optimizer and training. So they use AtomW, which I'm proud to say I already have a video on. So if you're interested in looking at that video, then please do. And in terms of training, they use BF16 for the training itself. However, when we accumulate gradients, this is done in floating point 32, which has high precision. And my hypothesis for why this is done is to prevent numerical underflow. Notwithstanding, I think nowadays, so that's to say 1 year later, because this paper was published in January 2024, so it's February 2025 now. So a long time ago is 1 year in LLM history. And now I think we can completely train and accumulate gradients in BF16, but at the time they did accumulate gradients in floating point 32 in order to prevent numerical underflow in the accumulated gradients. Okay, so they have some observations about the scaling laws. I didn't find this section too interesting since I myself don't train very large LLMs, but you can see that they just perform a grid search, and one grid search is for the batch size. Sorry, one axis is the batch size, another one is the learning rate, and they give the performance, and it's given in the units of floating point operations per token. So they motivate this metric instead of just parameter count as a better way of determining how a model will scale and generalize with the increase in parameters. But once again, instead of having parameters on the x-axis and saying, okay, parameters go up, generalization goes up, and so does performance, instead they say flops per token goes up, then so does performance. So they just claim that this is a better metric compared to raw parameters, and so be it. So they also have a section on alignment. We can skip all this because once again, it's just about the scaling hypotheses that they produce. And so this will be our last section in the video. However, it is quite interesting. So first of all, they mentioned gathering 3,868 Chinese and English prompts for detecting repetitive behavior. So what does this mean? In essence, when we have a text generation, the model will output the end of sequence token once it's finished output generation. However, in a weaker or less trained model, there is the chance that it never outputs this last token and just continues spewing out text. And the repetition ratio, which is described here, is simply how many times when you prompt the model does it do this repetition. And what they have highlighted is that when we have mathematic supervised fine-tuning, this ratio goes up. And this is because if you have a weaker model, then while it's trying to understand what's happening in terms of reasoning during the math problem, it doesn't yet know how to reason through it. But there's lots of common patterns in math. So as you can see, like the similar patterns. So it'll just continue to spew out these similar patterns. And I was unaware of such a problem before reading this paper. So I just wanted to highlight this to you in case you haven't heard of such a problem before. And once again, for their alignment, they use a 2-stage fine-tuning process instead of simple supervised fine-tuning. So first they do the supervised fine-tuning, but then it's the direct preference optimization. If you'd like to read this here, you can go ahead, and I'll also link the paper to DPO, but that's not the focus of this summary that I'm giving today. But just know that supervised fine-tuning plus DPO does reduce the repetition. However, it does slightly decrease the benchmark scores. And this is a very significant point in conclusion because it highlights the alignment performance trade-off. So I talked about the memory compute trade-off today, but also don't forget the alignment performance trade-off. The more aligned the model is, in general, the less it will perform well. So this is another trend which is pertinent in the realm of large language models. There you have it. So that was a very quick rundown of the Deepseek LLM, which was the first paper publicly made by Deepseek. And stay tuned for the future videos where I'll be discussing the more novel Deepseek contributions.
What are you doing؟ خب من دارم این ویدیو ضبط میکنم، داری دیسترکت میکنی.